Hi, myself Dr. P. Lakshmi Devi, Professor, Department of ECE, St. Peter's Engineering College. Already have completed a number of videos on image processing, digital image processing. And this regard image restoration topics I would like to cover here. Already in the image restoration also, aperiodic noises how you are going to remove with this image restoration concepts. So image restoration or image restoration both are appears to be the same. How you are going to reconstruct the image by minimizing its noise as well as any disturbances occurs in that particular images we are going to take care of in this image restoration concepts. As a third unit of digital image processing, we have image restoration, and this periodic and aperiodic noises how we are going to minimize. These are the main two categories we have in the image restoration. So aperiodic noises how you are going to remove, that already I covered in the last video, and periodic noises how you are going to remove, that will cover in this presentation of video. So periodic noises removed by a frequency domain filters. Periodic noises are removed by frequency domain filtering concepts. What are the different filtering concepts we have, and what's the hierarchy of this total image restoration concepts that we will see in today's topic. So basic frequency domain filters we have in the image restoration: band pass filters, band reject filters, notch filters, low pass filters, and high pass filters. Let us see here first, before going in depth of these different types of filters, types of image degradations. Types of image degradations hierarchy, if you observe in this, due to blurring there is a chance to have degrading the quality of an image, and due to effect of different sort of noises there is a chance to have degrading the quality of an image. Suppose due to blurring, what are the reasons for occurring blur in the images? Due to motion blur, lens blur, as well as point spread function of the cameras, there is a chance to have blurring effect in the images at the time of capturing. So how we are estimating that point spread function? That is the method of estimation, and this method of estimation have been divided into the three types, that is by observation, by experimentation, by mathematical modeling. The noises basically we have categorized into the two types, that is due to electronics of camera. At the time of conversion of photonic energy into electronic energy, there is a chance to have this particular noise to be added in that. That is due to electronics of camera, and due to a quantization process at the time of converting actual capturing of an image into digitized form, the quantization gets taking place. That is converting of an image into a digital form. This quantization, at the time of quantization, some sort of noise to be included in the images. That is also one type of noise to be considered. Totally, what are the different noise models to be encountered in the generating or occurring of noises in the images means different noises. Those are basically categorized into aperiodic and periodic noises. Aperiodic noises or random noises, we'll call it as. Those are Gaussian noise, Rayleigh noise, Erlang or gamma noise, exponential noise, uniform noise, impulse noise, or salt and pepper noises. These are random noises, and periodic noise is another category. So this hierarchy given in this particular slide. Suppose if you see what are the different methods we are making use of for minimizing of random noises means arithmetic turbulence model, ideal low pass filters, Gaussian low pass filters, Butterworth low pass filters, and linear motion blur models. All these things we are minimizing through a direct inverse filtering concepts. And restoration, that is periodic noises how you are going to remove means a restoration of noise only through algorithms. That is only noise if you have considered what are the different algorithms we have. In that case here restoration of an images, if the image is affected only with the noise, how you are going to restore that image? That particular concepts are divided into the two types. One is spatial based method filtering and the one is frequency based method filtering. In this spatial based method filtering, already we observed the different types of spatial based method filterings. Those are again categorized into the two types, mean filters and statistical based filters. Mean filters actually categorized into the four types, that is arithmetic mean filters, geometric mean filters, harmonic mean filters, contra-harmonic mean filters. This already I have shown you in the last video, and statistical based filters are also completed. Those are median filters, max or min filters, midpoint filter, alpha mean filters. Then coming to this frequency based methods, periodic noise reduction and periodic noise reduction filters only will concentrate on today's video. Those are band reject filters, band pass filters, notch filters. Already high pass and low pass filters completed in the last discussions only, but for understanding sake here I would like to show this high pass and band pass filters also, high pass and low pass filters. After completion of this particular hierarchy, then if you enter into the, suppose if the image is degraded due to the point spread function of the cameras as well as the noise, if both are gets affected for degrading the image, then what are the different methods we have for retrieving the image from these particular degradations? That is minimum mean square error filter as well as constrained least square filtering concepts. Geometric mean filter, and this minimum mean square error filter is also named as Werner filtering concepts and constrained least square filtering concepts. These two are also we'll see in the consequence videos in the next. Then coming to the actual categorization of removing of periodic noises by frequency domain filters. The first one here you can observe the band reject filters. Band reject filters, the name itself suggests us which type of filtering components we are going to minimize or we are going to remove. That is a specified band of frequency components. If you have removed from the existing frequency components of an image, that will call it as band reject filters. Because of frequency domain, here we are discussing in terms of frequency components. Suppose if the image in spatial domain means that concepts are different, actually what we are discussing now. It removes a band of frequencies about the origin of the Fourier transformer. Let us see first ideal band reject filters. The name itself gives ideal. Ideal means practically there is no chance to exist and there is no chance to appear any such type of ideal things in the nature. But still, for the reference sake, we'll consider ideal low pass, ideal high pass, ideal band pass, ideal band reject, like this. Now, an ideal band reject filter is given by the expression h of uv as a transfer function of this. H of uv is equals to 1 if d of uv is less than d naught minus w by 2, where d of uv is the distance from the origin of the center frequency of the rectangle. If you consider from the center to the distance d of uv, and if d of uv is less than d naught minus w by 2, the total width of the band is w. If we have divided that into minus w by 2 on left hand side plus w by 2 on right hand side, then within this d of uv is the distance from the origin. If you consider, if it allows that particular band reject filter, band of frequencies only it reject, the remaining all the frequencies it allows to pass through it. Because of that, here the transfer function how we are defining means h of uv is equals to filter transfer function. We named it as h of uv. It allows d of uv if it is less than d naught minus w by 2, and it allows all the frequencies if d of uv is greater than d naught plus w by 2. If d of uv is lies in between d naught minus w by 2 and d naught plus w by 2, then it rejects that particular specified band of frequencies. That we named it as a transfer function of band reject filter. W is the width of the band, d naught is the radial center of the frequency rectangle. Let us see here as a pictorial representation of band reject filter. Let us observe this h of uv, the transfer function, the band reject filter. It allows a particular band of frequencies not to transfer. The remaining all the frequencies it allows to pass through it. This particular rectangular diagram, it shows the lower portions only it won't allow to pass, the remaining all the portions it allows to pass. That is, on positive frequencies and negative frequencies, we are representing the center for rejecting u0 v0 in the positive side and minus u0 v0 on negative side. So h of uv on y-axis, d of uv on x-axis. So transfer function h of uv in this particular notation, how you are representing means 0 whenever d1 of uv is less than or equals to d0, or d2 of uv is less than or equals to d0. Otherwise it's a 1, because a particular band of frequencies only it reject, otherwise it allows all the frequency components. So d1 of uv is equals to, how we can calculate, square root of u minus u0 whole square plus v minus v0 whole square. d2 of uv is equals to u plus u0 whole square plus v plus v0 whole square, where d0 is the local frequency radius, u0 v0s are local frequency coordinates, minus on negative frequencies and plus on positive frequency components. Then coming to the practical, ideal case it's over. Then practical case of band reject filters, we have two types of band reject filters. Those are Butterworth band reject filter, Gaussian band reject filter. That is Butterworth band reject and Gaussian band reject. These are the two practical band reject filters we have. Let us see here the transfer function of band reject filter. H of uv is equals to 1 by 1 plus d of uv into w by d square of uv minus d0 square to the power of 2n. This is the transfer function. And similarly for the Gaussian band reject filter, h of uv is equals to 1 minus exponential of minus 1 by 2 into d square of uv minus d0 square by d of uv into w to the power of square. So in this, the filter, how it is actually functions and how it removes the noise components, and that particular frequency domain representations, and sinusoidal noise, how it is actually removes with this band reject filters. Now we can observe with some sort of images here. Actually it shows some impulse forms whenever we can observe the frequency domain representation of this band reject filters, either in the Butterworth or in the Gaussian forms. These particular responses we can observe in this representations of the figures. That is, from left to the right, if you observe the perspective plots of Gaussian band reject filters, Gaussian and Butterworth band reject filters. But here, left to the right, if you observe ideal Butterworth filter, ideal one is the first one, A is the ideal one, Butterworth order 1 is the second figure, that is a B, and third one is Gaussian band reject filter. So in what way we have the difference between these perspective plots of ideal case, Butterworth case and Gaussian case. Ideal, we have exact edges for removing of frequency bands in ideal Butterworth case, and if you observe ideal band reject filters, and if you observe the practical cases of Butterworth with an order of 1 and Gaussian band reject filters, there is some change on cutoff frequencies of these, but more or less that removing of frequency band appears to be the same, but the set of frequencies and allowing of low frequency components gets varies based on order of the filter in case of Butterworth. Coming to this particular practical way of observing the difference of using this band reject filters, let us observe the first figure. That is, image was actually corrupted by some sinusoidal noise in the first figure A. Then B figure is at the spectrum of frequency domain representation, or we can say the spectrum of the figure A. Then Butterworth band reject filter, if you observe as a two-dimensional view of image, that's a C figure, that's a Butterworth band reject filter. If you have represented that figure as an image, it appears to be a ring. That black color indicates we are removing that particular frequencies and remaining all the frequencies it allows to pass through it. Then if you have done the convolution between this particular frequency domain representation of input image as well as Butterworth band reject filters, then output image is the D figure, that is the resultant of filtering concepts. This is removing of appearing of sinusoidal noises with reference to the first figure. This is actually the original image courtesy of NASA. Then removing of periodic noise by frequency domain filters. First the band reject filters we have completed. Then you go for the band pass filters, notch filters, low pass and high pass filters. Now let us see the band pass filter here. So the name itself suggests us it allows a particular band of frequencies and remaining all the frequencies it attenuates. The function of a band pass filter is opposite to that of band reject filter. It allows a specific frequency band of image to be paused and blocks the rest of the frequencies. How you are defining the transfer function of band pass filters means HBP of UV, that BP denotes band pass, is equals to 1 minus of band reject of UV. The transfer function of band reject filter, if we have subtracted from the total image, that resultant gives band pass filter transfer function, that is a HBP of UV, HBR of UVs. Then coming to the next, band pass filter perspective plot, if you observe at the three-dimensional view in the first figure, H of UV plot with the UV dimensions on respective coordinates. Band pass, it allows that particular band pass and reject all the other frequencies. The transfer function how you are defining means it's an opposite to the band reject filter. H of UV is equals to 0, D of UV is less than or equals to D naught minus W by 2, and it's also 0 if D of UV is greater than D naught plus W by 2. But when it allows to pass through it means whenever D of UV lies in between this D naught minus W by 2 and D naught plus W by 2. So in this way just we are defining the band pass filter transfer function H of UV. So here D of UV is equals to the square root of U square plus V square. As usual, D naught is the cutoff frequency and W is the bandwidth. As a two-dimensional figure, if you observe H of UV on y-axis, D of UV on x-axis, this is actually a two-dimensional frequency representation of band pass filtering. It allows a particular band of frequencies, and before that frequencies and after that frequencies it won't allows, it rejects. This is the notation of the two-dimensional as well as perspective plots of band pass filtering concepts. Now let us see the next filter, notch filter. Notch filter rejects, a notch filter passes. There are two types of notch filters, that is notch pass filters, not reject filters. The basic difference I would like to identify here in between the notch filters as well as band filters. Band pass filters and notch pass filters. Band itself gives a particular band of frequencies we are either allowing or rejecting. But here the notch filters indicates a specific frequencies only we are allowing. In such case we'll call it as notch pass filter. A specific frequency only if you are rejecting, or if you are attenuating, that will call it as notch reject filters. So notch filter rejects, notch filter passes frequencies in predefined neighborhoods about a center frequency. That is, due to the symmetry of the Fourier transform, notch filters must appear in symmetric pairs about the origin, that is on negative frequencies as well as on positive frequencies. Now the transfer function of an ideal notch reject filter of radius d naught with centers A of u naught v naught and by symmetry at minus u naught v naught is, suppose if you consider from its center frequency to the distance of d naught and positive frequencies of u naught v naught and negative frequencies of minus u naught and minus v naught, then d1 of uv is equals to square root of u minus m by 2 minus u naught whole square plus v minus n by 2 minus v naught whole square. From its center to the actually middle of the image with the size of m by 2 and n by 2. With this, d1 of uv have calculated. Similarly, d2 of uv is equals to square root of u minus m by 2 plus u naught whole square plus v minus n by 2 plus v naught whole square. So local frequency filtering concepts, how you are going to show here means, this is actually it's not notch pass filters, but this one is showing actually band pass filters only. But local frequency notations, local frequency filtering concepts, here you can see with the d1 of uv is equals to u minus u naught whole square plus v minus v naught whole square, and d2 of uv is equals to u plus u naught whole square plus v naught whole square. D naught is the local frequency radius, v naught and u naughts or u naught v naughts are local frequency coordinates. Coming to the ideal, Butterworth, Gaussian notch filters. Notch filters are also ideal notch filters, Butterworth notch filters, Gaussian notch filters. The transfer function of these notch filters here I am giving. H of uv is equals to 0 if d1 of uv is less than or equals to d naught, or d2 of uv is less than or equals to d naught, or otherwise 1. That is notch pass filters. H of uv is equals to 1 by 1 plus d naught square by d1 of uv into d2 of uv to the power of n. Then transfer function of Gaussian notch filter, h of uv is equals to 1 minus exponential of minus 1 by 2 d1 of uv into d2 of uv by d naught square. So these are the different transfer functions of ideal, Butterworth and Gaussian notch filters. Perspective plots here you can observe ideal, Butterworth and Gaussian notch reject filters. Notch pass filters and notch reject filters. How you are going to show the difference while observing the perspective plots of these filters means, in the perspective plots, whenever we are showing the exposed areas towards downward direction, that itself indicates it's a rejecting phenomena. Towards upward direction, that itself indicating pass, that is notch pass filters representation. So the first one is ideal, that's why we have sharp edges for the ideal case of notch reject filters, and Butterworth filters we have very curved shape of this particular Butterworth filters. By increasing the order, it's actually increases the blurriness, and Gaussian notch filters, it's having very steep edges as compared to the Butterworth filters. So like this you can show the difference between the notch filters, practical as well as ideal cases. This one is notch pass filter. Notch pass filter transfer function we are denoting of HNP of UV is equals to 1 minus of notch reject filter transfer function HNR of UV. Similarly, we observed in the band pass band reject also. The same thing here, HNP of UV is transfer function, that is notch pass filter transfer function, can be obtained from a corresponding notch reject filter with this transfer function of HNR of UV, that is subtracting from the full image of 1. Then notch filters, in the ideal case, original image can be restored if the noise can be estimated completely. That is how we are representing these particular concepts, in the sense noise can be partially estimated, so restored image may not be the same as original image at any cost, whatever the mechanism you have used for restoring the images. In general, we are representing f of xy is equals to g of xy minus eta of xy. So for restored image representation, we are denoting the restored image as f cap of xy is equals to g of xy minus eta cap of xy. So where eta cap of xy is equals to inverse Fourier transform of h of uv and g of uv. This is the way of evaluating the noise, but how extent the noise can be estimated, how prompt we are estimating the noise, it's everything is a doubt. That's the reason we'll go for a different types of filters for restoring the images. Here frequency band low pass filters. Suppose if you observe here low pass filters concept, after the band pass and band reject, notch pass and notch reject filters, here we'll observe the low pass filters. So what type of information we can observe here with this different frequency bands and percentage of energy enclosed in this particular concentric circles of low pass filters. Let us see here on left hand side we have an image and right hand side the frequency Fourier spectrum of that image. So in this, the center to the extreme ends we have different concentric circles. And this concentric circles, the center circle, the first and innermost circle can have, which is very small in the nature, it's having 90% of energy is enclosed in that small circle. Power enclosed in the small circle is 90%. Then second circle, totally it's having 6 concentric circles. Then second circle having 95% of energy, third circle having 98% of energy, fourth circle having 99% of energy, fifth circle 99.5%, and sixth circle, that is at most orbit or the circle, consists of 99.9% of energy. What we can observe in this particular circles and enclosing power relevant to the image, in the sense here we can observe with this example. Ideal low pass filter with this concentric circles, how we can observe the image with this center small circle, the amount of energy, even though it consists of 90% of the power enclosed in that small circle, but if you observe that 90% of an image, it's a totally blurred image with the first figure. And the second figure with the second concentric circle 95%, it gives somewhat a better as compared to the first figure. Then third figure 98%, still it increases the structure appearance and objects detection in the 99%, and the 99.5%, the fifth concentric circle, still it increases identifying of objects in the image, the 99.9%, the last circle. With this we can understood like concentric circle radius, if it is increases, we are in a position to minimize the blur and maximize the identification of objects which lies in the images. Let us observe this particular image. This is totally appears to be blurred image, but how you are observing this image, this appears to be a skull of a human. But actually what is this image? Let us see in the next figure. Let's see. Once we have restored this image properly, then this is actually the figure. A girl, a lady is sitting in front of actually dressing mirror. This is actually image. Because of that blurriness, it appears to be the skull of a human. These are the actually exact faults we are identifying with the capturing of images because of problems at the time of capturing of an image. Let us see here the low pass filter with some other example. Spatial domain, we are representing an image with f of xy. In the frequency domain, we are representing that as f of uv. And g of uv is actually the reconstructed image is equals to, or g of xy is actually degraded image is equals to f of uv convolution of h of uv, that in the spatial domain, but that we are representing the frequency domain as a multiplication f of uv into h of uv. So g of xy, from this particular g of uv we can reconstruct the g of xy in the inverse Fourier transform with the inverse Fourier transform phenomena. The same thing if you observe here, f of xy is actually the spatial domain, and for frequency domain or Fourier transform of this particular f of xy is equals to frequency domain representation having some concentric circles, and wherever we are actually concentrating, accordingly we can neglect or we can remove the things. Then we have the reconstructed image here. Suppose if we have given importance to the second concentric circle and extracting the information enclosed in the second concentric circle only, then definitely that image have some blurriness that appears after reconstruction and after inverse Fourier transform as a g of xy, as in the fourth figure. Definitely it consists of some blur in this. So ideal low pass filter and the high pass filters here you can observe. Ideal case of low pass filter transfer function, how you are defining, means h of uv is equals to 1 if d of uv is less than or equals to d naught, 0 if d of uv is greater than d naught. That is, d of uv is equals to square root of u square plus v square. D naught is the cutoff frequency. Let us observe this perspective plot on UV UV axis, like h of UV is on y-axis. This is a perspective plot of ideal low pass filter, which allows only low frequency components which are closer to the center frequency. Then this is a plot of h of UV as a two-dimensional domain. h of UV is y-axis and d of UV on x-axis. So this is actually the low pass filter ideal characteristics of the ideal frequency characteristics of the low pass filter. Let us observe here ideal low pass filter with the different concentric circles, how you are extracting or how you are restoring an image with increasing the concentric circles. Let us observe the second, fourth and sixth concentric circles here given. 98.65, 99.37 and 99.7% of power enclosed in the concentric circles, and corresponding restored images gives this type of quality. Here we can observe with increasing the concentric circle radius, automatically you have the better clarity in the reconstructed images. So this particular problem, we'll call it as actually the ringing problem or ringing effect. With minimizing the concentric, or by considering the small circles and extracting the information and applying the inverse Fourier transform and observing the blurriness in the images, that effect we'll call it as a ringing problem effect. So g of uv is equals to f of uv. This is actually the frequency domain. Convolution in the spatial domain is actually multiplication in the frequency domain. So g of uv is equals to f of uv into h of uv. So here convolution theorem is applicable. If you go for a spatial domain, it's actually the convolution theorem. G of xy is equals to f of xy convolution of h of xy. Now let us observe here h of uv is a transfer function. By applying inverse Fourier transform for this is actually the sync pulse, sync waveform. So h of xy, it's a sync signal. Here you can observe that particular effect, we'll call it as a ringing effect. If distance d naught, if it is increases, the ringing radius is decreases, the blurriness is decreases. Here you can observe the Gaussian filter. A Gaussian filter as a practical low pass filter. The perspective plot as a three-dimensional view, here you can observe on UV dimensions, two-dimensional h of UV, but this observes this perspective plot, and this is a two-dimensional view of cross-sectional view of Gaussian practical low pass filter, h of UV, d of UV on y and x axis respectively. The practical low pass filter. In this case, h of uv, how you are defining, means h of uv is equals to e power minus d square of uv by 2 d naught square. D of uv is equals to square root of square root of u square plus v square. Then softer blurring plus no ringing. That means softer blurring plus no ringing. If you go for the practical case of low pass filters, the blurring, it's actually decreases, and ringing also minimizes in case of practical cases of low pass filters. Let us see this, a Gaussian low pass filter. There is no any sharp edges like ideal low pass filters in this concentric circles. Definitely the amount of power enclosed on these concentric circles of low pass filters is also increased as compared to the ideal case of low pass filters. That's why this lowest circle 99.44%, 96.44%, then the next fourth circle and sixth circle having 99.11%. 99.11%. So these are Gaussian low pass filters as compared to the ideal low pass filters. We can observe here the clarity of this Gaussian low pass filter is increased tremendously compared to ideal case of low pass filters. So ideal high pass filter, here you can observe as compared to the low pass filters, h of uv is equals to 0, d of uv is less than or equals to d naught, 1, d of uv is greater than d naught. D of uv is equals to square root of u square plus v square, where d naught is equals to cutoff frequency. It is an opposite to the ideal low pass filters, where it allows the frequencies in the low pass. Here it rejects that frequencies. Other frequencies are allowing. This is a perspective plot as well as the cross-sectional view of ideal high pass filters. High pass Gaussian filter, practical high pass Gaussian filters. This particular filter doesn't consist of sharp edges for allowing of frequencies towards high frequency components. We can observe the sharp edges, slowly varying of a curve in this case of high pass Gaussian filters, which are practical high pass filters, where h of uv is equals to 1 minus e power minus d square of uv plus 2d naught square, where d of uv is equals to square root of u square plus v square. And high pass filtering concepts, here we can observe with the figures. Original one is this one. With the high pass filtering concepts, we are extracting the main high frequency components of this. Those are edges information here we have extracted as compared to the low frequency components. High frequency emphasis is another concept in this high pass filtering. That is, original one, if you have added with the high pass filtered concepts, that is called high frequency emphasis. Let us observe the difference. High frequency emphasis emphasize high frequencies, that is maintain low frequencies and mean, that is h dash of uv is equals to k naught plus h of uv. Typically k naught is equals to 1. Then in this case h dash of uv, cross-sectional view of high frequency emphasis we are showing like this. That is, it allowing low frequency components as well as the mean of high frequency components after the d naught, which improves the clarity in this high frequency emphasis as compared to the high pass as well as low pass. Let us observe here some memograms as well as some cameraman photographs here. Memogram in the first one, original is first one, and second one is high frequency emphasis. So that improves definitely the clarity in the high frequency emphasis as compared to the original. And the second figure, cameraman, if you observe, original image is this one and high frequency emphasis image is second one. This still improves some clarity compared to the first one. High pass filtering, original high pass emphasis filterings. This is original one, high pass emphasis. High frequency emphasis, if I have added with the histogram equalization, this is the still improves the clarity. With this example, we should understand how we are applying this different techniques in the image restoration in order to retrieve as improving the quality as possible with this particular different phenomena. Okay, so this already completed. So with this I hope you are understanding the concepts of image restoration, how you are removing the periodic noises with the frequency domain filters with a given hierarchy. Okay, thank you.